Hello, AP Chemistry, and welcome to section 15.6, where we talk about Q versus K. So K, equilibrium constant, right? And this is our equilibrium expression, where it's our products raised to their respective coefficients over the reactants raised to their respective coefficients. Bearing in mind that when we solve for K, these have to be equilibrium concentrations, meaning these are not initial concentrations. Okay, these are the concentrations when equilibrium has been reached. Now, Q is like an instantaneous picture of where my reaction is. And oh my gosh, it is also products raised to their respective coefficients over my reactants raised to their coefficients. Now, this, though, is an instantaneous view. Okay? Meaning these can be initial concentrations, these can be almost at equilibrium concentrations, these can be any concentrations you want them to be, right? If we label them with a Q. Okay? Now the point is that we can compare Q and K to talk about where a reaction is and where it is heading. Okay? I should come up with something else. Right. We can use right. All right. So K again, equilibrium constant. It is a constant for any reaction at a given temperature, right? If I take a look at K, which is where a reaction is at the moment, I can compare these two values to see where a reaction is heading, right? Now, if we think about the fact that K and Q, right, are really just, again, the relationship between product and reactant, right, at its essence, right? Then if we're talking about Q versus K, if Q is less than K, right, that means we have to be heading in that direction, right? So if Q is less than K, right, that means we need to increase, let's write this here too, right? If Q is less than K, we need to make it bigger, right? And that means make more product, yes? Which is what this scenario is saying, right? If my Q is greater than my K, that's kind of like saying I have too much product, so I need to consume that to make my reactant, yeah? Right? And that's what all this analysis is saying, right? And that's what all of this is saying, which I think is really reasonable, right? And it's really logical if you just remember that my Q expression and my K expressions are really just a relation between product and reactant, right? So then if Q is too big, how do we make it approach K? If Q is too small, how do we make it approach K? All right, next up, practice problem. So here it says, we want to, at blah blah, the value of Kp is this. Okay? Calculate the value for Q and predict the direction if the initial partial pressures, right? So initial is the key word with all of this, right? So I would plug them into my Q expression, and then like I did on the previous page, I would compare my Q versus my K. Yes? All right, next up. Here, it says that at 500 degrees, the reaction blah has a Kp of this. In an equilibrium mixture, the partial pressures of PCl5 and PCl3 are those. What is the partial pressure of Cl2? So what are we really doing here? Right. We already have our K value. We have two of my pieces of information. We're solving for X. Yeah? All right. Next up, it says for the equilibrium blah, the equilibrium constant is this. A gas cylinder at 500 is charged with PCl5 at an initial pressure of this. And I want to know my equilibrium pressures of everybody else. So here, we are monitoring change, right? Whereas here, there's no change, right? We're already at equilibrium and we want to know the last piece, right? Here, we know all of my initial pressures, which means we can do a Q versus K, right? Here, though we're not asking about which direction is it going to move, right? We are asking what the equilibrium pressures are, right? Which means that there's going to be a change in everybody's pressure until we reach equilibrium, which means that this should go ding, ding, ding in your head as a Rice table problem, right? Where we're going to start with our equation, which says PCl5, PCl3, and Cl2, all of which are gaseous. And initially, I know that I have 1.66 atmospheres of that, which means what about these? Right. I know that I'm going to lose some of that. I'm going to gain this, and I'm going to gain this, right? And again, that's based on the relative stoichiometry. okay? Which means that my equilibrium concentration is going to be 1.66 minus x, and this is going to be x and x, right? Now, if I think about my K expression, right, I know that K is equal to PCl3 times Cl2 over PCl5. And currently, right, based on what I know, that's going to be x times x over 1.66 minus x. And all of that's going to be equal to my K value that I already know, right? So we would set all of this up, and then, right, this is one of the only times that I think it's okay to use that solve for x feature, right? Nobody wants to write out the quadratic, and there's really no sense, and there's no need to waste that much time, right? This is one of those times where once we get to this part on your AP exam, right? For example, you could just put a little note here that says using solve for x feature, and then write down what your x equals, right? Now, some of you might be like, oh, but if I do that, aren't I going to get two values for x? Yes, you are, right? Only one of which will make sense, though, right? For example, if I get an x value that's bigger than this, does that make sense? No, right? That's not possible, right? So those are things to think about, right? That the x value that you're looking for is the one that's going to make sense within the structure of your problem. So then once I got x, I would solve for these, right? So x would be my concentrations for those, and 1.66 minus x would be my concentration for that. Does that make sense? All right. Now, I don't mean x can be bigger than this. I mean x couldn't be bigger than 1.66. That's what I mean. All right. Thank you for listening. Be good, and I will see you soon. Bye.